So today we're going to cover not quite all, but the overwhelming majority of circuit analysis you learned in Engineering 120 series in like 35 minutes. So let's start with Ohm's law. The experiment that I had you guys do on Friday, in which you took a test component let's call this component. That does not look good. Under test or CUT. So you took a component under test and you applied some voltage V S across it. You measured the voltage V test across it. And the reason why I made you measure the voltage using a multimeter as opposed to just using the output of the supply is because, well, these supplies are very, very cheap. And some of you may have observed that the multimeter reading and the voltage reading on the supply might have varied by as much as 400 millivolts or 0.4 volts. So using an actual piece of test equipment was useful there. So anyway, you applied some voltage with our power supply. You measured a quantity V test and you measured a quantity I test. This is the experiment using much fancier equipment that a German physicist by the name of George Simon Ohm did way back in the 1860s. And he found, as hopefully most of you found, that there was a proportional relationship between that quantity V test and that quantity I test. So what you should have observed when you did the experiment was something like this. So if the test voltage was on the horizontal axis and the test current was on the vertical axis, you should have had something like this, where this slope was I test over V test, right? Simple linear relationship. George Simon Ohm defined that constant of proportionality V test divided by I test to be the resistance of the material that he was testing. We can actually define a second constant of proportionality here. The ratio of I test divided by B test will be G, where G is what's called the conductance. R is the resistance. Okay. So we represent resistors in a circuit with the following symbol, where resistance has units of ohms, which is a volt per amp, And we represent conductances in a circuit by literally the exact same symbol, because we have to make things confusing. Where G is exactly equal to 1 over R, so it has units of Siemens, capital S, which is identical to the inverse of an ohm, or amps per volt. Okay. All right, so let's talk about what resistance is, and it's probably easiest to quantify by what you use them for back in the 120 series. So I want to say probably your maybe first or second day of class in engineering 120, for those of you that can remember it. Or at least this is what happened when I taught it. You made an LED blink, right? You made a really simple circuit containing just a resistor and an LED in series. And you sent a 5-volt output, and every time your output was 5 volts, the LED turned on, and every time the output was 0 volts, the LED turned off. What was the purpose of the resistor in that circuit? Anybody hook up something and apply 5 volts directly to the diode? If you guys didn't do that, then you paid much better attention to the instructions than any of my freshman classes ever did, okay? The purpose of the resistor there was to limit the amount of current that flowed through the LED so that it didn't burn out, okay? So resistances, or resistance, is a material quantity that measures how difficult it is pass current through a component. And similarly, conductivity is a material quantity that measures how easy it is to pass current through a component. So I believe in that very first, I don't even know if I can call it an experiment that many of you did back in Engineering 121. I want to say that you were supposed to hook up a 220 ohm resistor to that LED. And if you did correctly hook up a 220 ohm resistor, you observed that the LED shone very brightly. Some of you, I'm not saying any of you in particular, but I know that I certainly had a number of freshmen who did this, misread the colors on their resistors and all that kind of stuff, and accidentally connected, say, like a 20 kilo ohm resistor, a much higher resistor value, and observed that their LED shone very, very dimly. So you could like kind of see that it turned on, but it was hard to see, and it was because that 20 kilo ohm resistor limited the amount of current by a much significantly higher amount than the 220 ohm resistor was supposed to. So resistors are all about limiting the amount of current, and conductances are all about helping current flow in a system, okay? So a couple of different tangent paths that I could take right here. Let's start with this one, okay? Resistances as a component level device are incapable of storing energy, okay? So a resistor will always absorb power and energy. The job of a resistor is to impede current flow by converting electrical energy into heat. Okay. So that's why for some of you that asked, I talked about probably not setting your test voltage higher than say 10 volts or anything like that, because resistors, if you drive a lot of current through them, can get very, very hot. So much so that they'll smoke and burn out, but they can definitely get hot enough to cause contact burns and all that kind of good stuff. The ability to convert electrical energy into heat is the principle by which electric heaters and things like that work. So if you come into my office, I've got two little space heaters. They have what's called nichrome wire in them as the heating element. And so what that is it's a particular type of wire with a pretty large resistance as compared to something like copper wire. And so when you drive current through it, it gets red hot. And then they use a little fan to blow heat off of that piece of wire. And that's what heats up a room, okay? But only certain materials can do that. Tungsten is another good one that can handle a lot of current. That's how not any of the lights in this particular room work, because they're all fluorescent, but your incandescent bulbs and all that kind of good stuff. They have a pretty, the tungsten filament has a pretty good high resistance, causes it to glow as current is passed through it, emitting light and all that kind of good stuff. Other things like copper have very, very low resistances. The way that you can determine what the resistance of a particular wire is governed by a mathematical equation that you guys actually learned back in Engineering 121, or at least it was taught in 121 when I taught it a couple of years back. So that equation is resistance R is equal to rho multiplied by L over A, where L is the length of a conductor, A is the cross-sectional area of a conductor, and rho is the resistivity of the material. So it's a material dependent property, right? So let's say that we had a wire. The total length of the wire is 10 meters. This wire is going to be what's called AWG number 18, which means that it has a diameter, D, of 1.024 millimeters. And it's going to be made of copper, which has a resistivity of 1.68 times 10 to the negative 8 ohm meters. So what I would like you guys to do is take a moment and calculate what the resistance of this piece of wire would be. Anybody get an answer yet? Bless you. Anybody got anything for me? Yes, sir. 0.204. Thank you, Kai. 0.204 ohms, or around 200 milliohms. So AWG number 18 wire is a couple of gauges larger than what comes in your jumper kits and all that kind of stuff that you used in your Engineering 120 series. So it's got a diameter that is very slightly larger, which means it's going to have a little less resistance, right? Slightly larger diameter means a slightly larger cross-sectional area, which means the resistance is going to be slightly less. That being said, what does the length of 10 meters, how does that compare to the lengths of wire that you guys use in any of these circuits that you've ever built? Much longer, right? Typically speaking, you're dealing with sections of wire that are a couple of inches long at the most, and a meter is a little bit over 3 feet. So we're talking about an astronomically larger, not an astronomically larger length, but a much larger length. So 10 meters of this wire has a resistance of 0.2 ohms. What's the smallest resistor that you guys ever built a circuit with? Somewhere on the order of 200 probably in your Engineering 120 series, okay? In this class, we might do a couple of experiments that use, say, like 10 ohm resistors and all that kind of stuff. But effectively, every resistor that we are going to ever build a circuit out of in this class has a resistance that is an order of magnitude or larger than the resistance of this incredibly long piece of wire. So in Engineering 120, you made an assumption that wires don't contribute any resistance. In truth, they do contribute some resistance, but it's just so small as to not matter in the overwhelming majority of applications. Unless you're doing high power electronics and stuff like that, the length of a wire isn't really going to matter. So for those of you that go into mechanical engineering and all that kind of stuff, and you're working on setting up and maintaining HVAC systems, you need to make sure that the wires that you use to power that guy aren't so long that they cause a significant voltage drop, which will make your HVAC system run inefficiently. But for the overwhelming majority of us, this is never going to be much of a problem. Okay. So in this class, for all of our circuit analysis that we are going to do, we are going to continue with the assumption that wires contribute no resistance because we've mathematically proved that they effectively do. So with that in mind, I have a couple of different little things here that I want to talk about before I move on to a different topic, okay? The first of which is the concept of short circuits and open circuits, all right? So a short circuit is nothing more than a section of wire, okay? It will have a resistance of 0 ohms, which means from Ohm's law that it must have a voltage drop of 0 volts across it. So in this class, any section of wire that's used to link two components together will be treated as a short circuit, which has zero resistance and no voltage drop over it. I know I'm saying this very slowly and all that kind of stuff. Doesn't seem like a particularly difficult concept, but I'd be willing to bet that some of your peers will forget it when it becomes important in a little bit. The exact opposite of a short circuit is the open circuit. We represent an open circuit by a pair of open terminals. So there's no connection. An open circuit has an infinitely large resistance. And thus, from Ohm's law, the current flowing through an open circuit, 0 amps. These are an idealized representation. Okay. What I mean by that is that if I take a battery or something like that, and I take a piece of wire and connect the positive polarity terminal of the battery to the negative polarity terminal of the battery, by definition, there has to be a voltage drop of whatever the battery is flowing across, or placed across that wire, observed across that wire, not flowing because the voltage doesn't flow. You'll probably see sparks and all that kind of good stuff if you do it. And the reason for that is the wire actually has some sort of finite resistance. Okay, it's going to be very, very small, but when you have a very large voltage drop, and large in this case is, you know, a volt or two over a very, very small resistance, that means that the current that's flowing through it is just going to be the maximum of whatever that source can provide. So for a AA battery, that's going to be a couple of amps. Not enough to do anything super harmful, could cause the battery to maybe explode. They can definitely get hot enough to like melt a battery pack and all that kind of stuff. I understand that you guys don't use the same battery packs that we used to in the 120 series when I taught it, but we used to have to tell the students before they did some soldering, never leave the batteries in your battery pack, because if the wires get crossed, you're going to wake up tomorrow, something's going to smell horrible, and your battery pack is just going to be this mangled mess of plastic. And some people wouldn't pay attention, and some people would have to go talk to Ashley and get a new battery pack. Similarly, we say that no current can flow through an open circuit, but that's not entirely true, as I'm sure anybody in this class who's ever used a blow dryer or anything has observed. If you plug in a blow dryer, you turn it on, you get it going, and then you unplug the blow dryer, what happens? Sparks, all that kind of good stuff. That's current flowing across an open circuit. It has a lot to do with electromagnetic induction, which we're going to talk very briefly about in this class. You'll learn about it in your Physics 202 class and all that kind of good stuff. But effectively, if the voltage is high enough, it can ionize the air and create a conductive path across an open circuit. Okay? So again, these are idealized representations that we're going to be dealing with in this class, but they are not hard and true rules for dealing with electricity, you know, out in the real world. All right, so the next thing I want to do is develop a couple of relationships. But before I do that specifically, I want to talk about Ohm's law and how it fits into the passive sign convention, because this is something that a lot of students get tripped up on. Because you guys learned, and we talked about earlier, I could rearrange this guy and say V is equal to IR all day long. There's not really an issue with that per se. But if I have a resistor R, like so, and I have a voltage drop VR across it, and a current of IR flowing into the positive polarity terminal, I can say that VR is equal to IR times R. But I take that same resistor, I have that voltage drop of VR across it, but now my current IR flows in the opposite direction. I will find that VR is equal to negative I times R. The reason for this is the passive sign convention, and effectively all this second condition means is that one of those quantities, either the voltage or the current, actually has to be negative. Because this guy is always, always, always going to be absorbing power, okay? So I'm pointing this out to you now because there are going to be times where you're going to have to make educated guesses as to either the direction of current flowing through a resistor or the polarity of the voltage drop over a resistor. And this is how you relate those two quantities, okay? So when the current is flowing into the positive polarity terminal, Ohm's law has a positive sign. When the current is flowing into the negative polarity terminal, Ohm's law needs a negative sign. Are we okay with that? All right, so, yes, sir. Correct, only for resistors.
Question. What was that rule called again?
That's just Ohm's law, but we're using the passive sign convention along with that. The passive sign convention was something that we talked about at the end of class on Friday. Is that right? Yeah. So we can use Ohm's law. Let me do this as a quick aside here. And say, rewrite our power equations, okay? So for a resistor, where this should just be IR times VR, we could rewrite this as VR squared over R, or IR squared multiplied by R. And in this case, obviously, the polarity of the voltage doesn't matter and the direction of the current doesn't matter because we're going to square it. So we're always going to get a positive value for the power, which is again just reinforcing the fact that the resistors are always absorbing power. For conductances, power is still simply the product of V times I. But now we'll see that we're going to have the voltage squared times the conductance is equal to the current squared over the conductance. Now, other than literally pretty much right now, I'm not going to mention conductances again in this class for about 7 weeks. Then I'm going to talk about them for about 5 minutes as part of a concept called impedance. And then I'm never going to mention them again. I have a bachelor's degree in electrical engineering, a master's degree in electrical engineering, and a PhD in micro and nano systems engineering with a focus on electronics. I can tell you definitively that unless you go into electrical engineering and do a lot of work with transmission line theory, conductance doesn't mean crap to you, okay? You're not going to see it very often. It is just here to annoy you in circuits 1 for the most part, until 3 years down the road for you EE students who might happen to take classes that talk about it, okay? So in this class, anytime you have a conductance, convert it into a resistance, and then go about your day. Make your life much, much easier. So simply take the reciprocal of it to give yourself the resistance value, and then just move forward as if it were a resistor, and your life will be so much easier. You won't have to remember all of these inverse relationships. You won't have to remember special rules for combining conductors or conductances as opposed to how resistance is combined and all that kind of good stuff. Everything's just going to be much, much easier if you take the reciprocal of it, say it's a resistor now, and chug along. All right. So before we move to our next topic, does anybody have any other questions regarding resistance and conductance? All righty. Oops, that's far too many pages. So the next thing that I would like to talk about is Kirchhoff's voltage law. So Kirchhoff's voltage law states the sum of the voltage drops around any closed path must equal 0. Mathematically, this just says that V equal to the line integral of E dot dl, which is our mathematical definition for voltage that we introduced the other day. And then that symbol on the integral means that we effectively go back to where we started from. So we do a line integral around a closed path. Since we are doing a line integral about a closed path for a conservative quantity, it must equal to 0. So this is the same as me saying, if I give this pen some kinetic energy by throwing it up into the air, it's going to lose all of that kinetic energy when it returns to ground and becomes still. Or if I give it potential energy by raising it up, it lost its potential energy when I put it back down. The exact same thing. Okay? So the sum of all voltage drops around any closed path, so it doesn't matter what path I take or anything like that, must equal to 0. A consequence of this is that when we have two elements in parallel, doesn't matter what they are, they must have the same voltage drop across them. Okay? So if I have an 8-volt source and a 15-ohm resistor, if I have my voltage drop VR oriented in this way, and I apply Kirchhoff's voltage law, how I like to apply it is I start in the bottom left-hand corner, and then I just go around the circuit in a clockwise fashion until I return to the node that I started from. I would see negative 8 volts. And it's negative because I see the negative polarity terminal of that 8-volt source first, plus VR is equal to 0, which means VR is equal to 8 volts. So again, these two are connected in parallel. because they share a top node and they share a bottom node, they have to have the same voltage drop over them. If I put another element in parallel, that one would also have 8 volts and so forth and so forth. So whenever things are connected in parallel, they have to have the exact same voltage. Okay. Now, that same voltage requirement means that the voltages need to be defined with the same polarity. So for example, let me erase this real quick. Let's say that I have put a 5 ohm resistor here, but I define the polarity over this guy. Let's call this VR1 now. This guy is VR2. Well, if I start at that same point here, and go around, my Kirchhoff's voltage law equation will look like -8 volts minus VR2 is equal to 0, which means VR2 is -8 volts. So we have the exact same magnitude of voltage, but we have an opposite sign because the polarity was defined differently. Everybody catching what I'm throwing here? All right. So let's talk about ways in which Kirchhoff's voltage law can be applied. All right. Let's say that we have the following circuit. Trying to think if this example problem might be mildly too difficult, but let's run with it. Okay. So we have a complex looking circuit here. All right. We have a dependent source in there, which this is probably your first time dealing with one. And then we also have what looks to be a voltage drop in the middle of the circuit over nothing, right? It's not a voltage drop over a single component. It can be thought of as actually a voltage drop over multiple components. This is an example of what's called a single loop circuit, okay? In this single loop circuit, all of the elements are connected together in series. So that 5 volt source is in series with the 10 ohm resistor, the 10 ohm resistor is in series with the 2 ohm resistor, the 2 ohm resistor is in series with the dependent source, and so on and so on. Because all of those elements share a single point of connection with no branching paths, everything is in series. Okay. So it stands to reason that if a current is flowing in this circuit, the same current flows through all of the elements. We'll prove that in about 5 minutes using a thing called Kirchhoff's current, right? So what I'm saying is, let's say that I have some current here, I. That same current I has to be flowing here, as well as here, as well as here, as well as here, as well as here, right? So that's one current I just circulates around that single loop because we know no current can branch off and flow through that open circuit in the middle because open circuit current has to be 0. So we can use a combination of Kirchhoff's voltage law and Ohm's law combined to analyze a gnarly looking circuit like this and actually come up with a result fairly easily, okay? So for example, if I write a Kirchhoff's voltage law equation around the perimeter of the circuit where I'm just following that current I along, what would I get? I'm going to pick on you, Skylar, if that's okay. So what would my KVL equation around the outside loop be? So 10 ohms multiplied by I. So what Skylar's doing here is just using Ohm's law and saying that since Kirchhoff's voltage law is all about adding up voltage drops, she's saying that the voltage drop over the 10 ohm resistor is simply that current I times the resistor value. Another way to think about it, sorry for interrupting you, is that she's saying that there's a voltage drop V10 here, a voltage drop V2 here, a voltage drop V5 here, and a voltage drop V8 there. And she's assumed that the current is flowing into the positive polarity terminal for all of those resistors so that she doesn't introduce a bunch of wacky negative signs all over the place. Okay, so, all right. Sorry for interrupting you there, Skylar. Is equal to 0 because we completed the loop. And now I can lump all this crap together, right? So I can say, let's see, 10 plus 2 is 12. Oh, sorry, that should be an 8, not a 9. I think that's just because you, no. I'll write it more clearly. That's my fault. So 10 plus 2 plus 8 plus 5 looks like 25 ohms times I plus 3 times Vx is equal to 5 volts. That's just rewriting that equation, grouping things together and all that kind of good stuff. Right? So right now we have one equation, but we have two unknown quantities. The current I and that voltage Vx. So what we can do is we can write another Kirchhoff's voltage law equation so that we'll have two equations involving I and Vx. So how do you think we can get another equation out of this? Pardon?
You go the other way with the current.
So if we go the other way with the current, that's just that exact same equation multiplied by a factor of -1. So it's not going to give us any different relationship, right? But what we can do is we can go across that Vx in the middle, okay? So Kirchhoff's voltage law is all about adding up voltage drops. It actually doesn't care whether or not current can flow, okay? So we can go across that voltage drop in the middle. So we could either do this loop or this loop, which would give us an expression, a second expression, which has a Vx in it and an I in it, okay? So which one do you guys want to do? The left-hand loop or the right-hand loop? The left, okay. Let's see. Maggie, can I pick on you? All right. So I want you to help me with my Kirchhoff's voltage law loop around the left-hand loop that I've kind of done in gray. All right. All right, go away, notification thing. It'll be 10 ohms times I, okay. And so now we're going across that Vx in the middle. So we see the positive polarity terminal first. So it's just gonna look like plus Vx. Because it's a voltage drop, we don't need to put a current or anything in there, right? Kirchhoff's voltage law is just adding up voltage drops. So plus Vx is perfectly okay. And now we're at this point right here, and we're headed to the left. What's next? Absolutely right. So we can rewrite this guy, and we wind up having 18 ohms times I plus 1 Vx is equal to 5 volts. And now we have two equations and two unknowns, right? Here's our first one. Here's our second one. So we can either suffer through substitution and all that kind of stuff, which for this one isn't going to be that particularly difficult, or we can use the fancy pants calculators that we all hopefully have at this point and just throw it in and solve our two equation, two unknown system. I'm much more inclined to use the calculator to do it than I am trying to remember how to do simple substitution. So if you have not yet figured out how to set up systems of equations on your calculators and solve them, you should work towards getting a lot of practice in that, because we're going to be doing it an awful lot. So I get current I is equal to 0.345 amps and a voltage Vx equal to negative 1.207 volts. All right, so in this particular circuit, we wound up applying Kirchhoff's voltage law twice. There were actually 3 different loops that we could have used. Really, we could have solved this using any 2 of them. I believe this problem to be a pretty significant step increase in difficulty from what you guys saw in your circuits, in your Engineering 120 series. This is more representative of what we are going to be doing. Not in any way, shape, or form saying all of our circuits are going to have dependent sources and all that kind of stuff to deal with, but a whole heck of a lot of them are. Okay, so I hope this made sense. And if not, flag me down after we finish up the lecture, and I'd be happy to walk you through what was going on and all that kind of good stuff again, work other examples and all that jazz. So another thing that I can say pretty definitively here is that anytime we have a single loop circuit where all of the elements are connected in series, Kirchhoff's voltage law that should be where you start your analysis, okay? That's usually going to be one of the easiest ways to analyze the circuit. And it's because there's a common current flowing through everything. So that you should be able to figure out pretty easily. All right. Any questions regarding Kirchhoff's voltage law and its application in this example that we used here? All right. So the next thing that I would like to talk about then is Kirchhoff's current law. There are three different ways that we can represent Kirchhoff's current law, and they all mean effectively the same thing, okay? So I'm going to start by drawing a little picture here. So I have a single node point in the middle, and then I have 5 currents flowing from elsewhere in the circuit. Some of them are flowing into the node, others are flowing out of the node, okay? So our first representation of Kirchhoff's current law, and it's likely how you learned it in the Engineering 120 series, is that the sum of all currents flowing into a node must equal the sum of all currents flowing out of a node. So using this particular formulation, we could say that I1 is flowing in, I4 is flowing in, and I5 is flowing in. So we can say that I1 plus I4 plus I5, which is the sum of all currents flowing in, have to equal I2 plus I3, which is the sum of the currents flowing out. So again, this is very likely how you guys learned Kirchhoff's current law in your Engineering 120 series. There isn't anything particularly wrong with this, and I absolutely wind up using this formulation sometimes. But we are going to use a tool called Nodal Analysis in just a little over a week or so. And it will be very beneficial for us to understand these next two formulations, because that's going to allow us to apply this very powerful tool without having a bunch of weird signs all over our equations, okay? So our second formulation, let's say that this just is going to be the sum of all currents flowing into a node must equal 0. So this doesn't mean I1 plus I4 plus I5 is equal to 0. What this guy means is that we should treat I2 and I3 as a negative current flowing in, because they're flowing out. So effectively, if we see a current flowing out, we can change the sign or change the direction by changing the sign. So it would look like I1 minus I2 minus I3 plus I4 plus I5 is equal to 0. Mathematically, this is absolutely identical to our first equation, except that we move the quantity I2 and I3 from the right-hand side of the equal sign to the left-hand side of the equal sign. Okay, nothing, mathematically, it's no different whatsoever, but how we're applying KCL is a little bit different, okay? Our third formulation is the sum of all currents exiting a node, flowing out of a node, must equal 0. So in this case, we would treat I1, I4, and I5 as a negative quantity because they are currents flowing in the opposite direction of what we want. So this would look like negative I1 plus I2 plus I3 minus I4 minus I5 is equal to 0, which is the exact same thing as what we got applying method number 2, except everything is multiplied by a factor of -1. Okay. So they're all mathematically equal. They're just different ways of thinking about the exact same thing. Okay. My personal preference is option 3, and it's because of doing nodal analysis. Okay. I will absolutely fall back on options 1 and options 2 whenever it suits me, but option 3 is kind of my default. What I would do if I were you all, when you're working a problem, literally kind of write things down. So if you're going to apply Kirchhoff's current law, write down all currents going in is equal to all currents going out, and things like that to kind of figure out which way you're going to do it and be consistent, okay? Because it's easy to make some simple mistakes if you flip-flop back and forth between the methods. So with that being said, let's say that we have, actually, before we do an example problem, let's talk about something else here. Okay. So a few minutes ago, we worked an example problem where there were multiple things connected in series. So let's call this guy element A and this guy element B. So if a current IA is flowing into element A, stands to reason that that same current IA is flowing out of element A. Let's say that we have a current IB flowing into element B, and therefore we have a current IB flowing out of element B. Okay, there's nowhere for any of the current to branch off, so all of it's flowing through the element. What can we say is the relationship between current IA and current IB? They have to be equal. IA must be equal. So all that means is that when two elements are connected in series, they have to carry the same amount of current. Okay. So that's another way for us to define whether or not things are in series. We talked about on Friday, no, we talked about last Wednesday, elements were considered to be in series if they shared a single point of interconnection with no branching paths. This is that situation exactly, but we can now expand it to contain multiple elements where let's say A was connected in series with B and B was connected in series with C, since if they all carry the exact same current, we can treat them as if they are all in series, okay? Which is exactly what we did in this example problem here. So we used Kirchhoff's current law accidentally just by using logic effectively. All right, so now let's circle back around to an example problem. So let's say I have the following circuit where I have a 7 amp source connected to an 8 ohm resistor connected to a 5 ohm resistor connected to a 3 amp source. And I want to figure out what this voltage Vx is. So we are going to use Kirchhoff's current law and Ohm's law to solve this guy, all right? We're also going to sprinkle in a touch of Kirchhoff's voltage law as well, but for just one very, very small part, okay? So let's start with the touch of Kirchhoff's voltage law part, okay? How are all of these elements connected? They're all in parallel. Since they're all in parallel, that means that all of them have a voltage Vx across them. Okay, that's our application of Kirchhoff's voltage law here. Just recognizing that since all of the elements are connected in parallel, they have to have the same voltage drop across them. So I'm going to apply Kirchhoff's current law to this circuit. So you guys tell me, we apply Kirchhoff's current law at a node. Should we use the top node or the bottom node? Top, okay. Should we use formulation 1, 2, or 3? 3, okay. So I'm going to apply KCL at top node. And I'm going to say currents leaving positive. Because that's what formulation number 3 does, treats the leaving currents as positive, okay? So, is the 7 amp current provided by the source on the left, is that leaving the node or entering the node, the top node? It's entering. So what sign should it get? Negative. All right, now we have the current through the 8 ohm resistor, okay? There's gonna be some current, but we haven't defined a direction yet, all right? So let's talk about what direction we should use here, okay? Now we don't have to do this, it will absolutely work out if we choose not to, but I would argue that we should choose a direction down in this case for the current flowing through the 8 ohm resistor. And the reason why I say that is because the 8 ohm resistor has a voltage drop of Vx across it with a positive polarity on top. So if we choose a direction down, that current is flowing into the positive polarity terminal, which means we don't have to introduce an extra negative sign to use Ohm's law correctly, okay? So I'm forcing it to behave with the current flowing into the positive polarity terminal to avoid getting a negative sign, because I know personally, I make lots of mistakes when there are lots of negative signs in a problem. So effectively, what we are assuming is that there will be a current I8 flowing down through the 8 ohm resistor, and similarly, there will be a current I5 flowing down through the 5 ohm resistor. And now we're just going to use Ohm's law to represent those currents in terms of that common voltage Vx. So how can I represent that current I8 in terms of that voltage Vx? Vx over 8 ohms, absolutely right. What about the current I5 flowing down through the 5 ohm resistor? Vx over 5 ohms. All right, so now I have the current from my 3 amp source. So what sign should it get? What was that? Positive. So from this, we're going to have Vx multiplied by 1/8 of an ohm plus 1/5 of an ohm is equal to 7 amps minus 3 amps. And we could now solve that common voltage Vx. And we get 12.308 volts. Knowing this, we could now figure out what every current in the system is. Here's how we can use Kirchhoff's current law as well as Ohm's law to analyze what's called a single node pair circuit. In a single node pair circuit, all of the elements are connected in parallel. And so, in my opinion, applying Kirchhoff's current law to a single node pair circuit is usually how you should start off your analysis. Okay. In your homeworks and stuff like that for the next couple of sets, I believe it literally explicitly says you have a single node pair circuit or a single loop circuit. On my exams and things like that, I expect you to be able to identify the circuit by looking at it to choose what type of methodology you want to use to solve. Okay. Let's see, it's 3:45. So 40 minutes left in class. All right, that's enough talking out of me for today then.